Everybody. I have one for you tonight. I guess it's a stated problem, and it's sort of clumsily worded, but I thought it was kind of interesting. So let's see if we can take a look at it here. Now, n is a natural number, a positive integer. And what we have here, this is kind of lengthier, but it says, suppose all the positive integer multiples or natural number multiples of n less than n minus 1 squared, n minus 1 quantity squared, sum to this strange number here, 1176n. You're supposed to find the value of n. Now, this one stumped me just a little bit because I thought multiples of n. Then it hit me. I says, oh, okay, n squared. N squared is a multiple of n. It's n times n, right? Now, what I've written here, just to kind of get our bearings, is this is the sum of the first n minus 1 multiples, meaning, 1n, 2n, 3n, all the way up to the multiple n minus 1 times n. Now, this is kind of an odd looking condition, so we had to figure out what it really means. And one way to see what's going on here is you can see that n minus 1 quantity squared is the same as n minus 1 times n minus 1. But this number right here, this multiple of n, the n minus 1 multiple of n, is a bigger number, and that's clear, isn't it? Because this is n minus 1 times n minus 1. Well, this is n minus 1 times a bigger number. So it's clear that we're going to be able to exclude this multiple. We're supposed to, all the positive multiples of n less than this. So this one's going to be excluded, all right? Now, it turns out the next one is going to get excluded too. The n minus 2 times n is going to get excluded also, because it's not too hard to see that n squared minus 2n, when you square this out, it's going to be necessarily less than this because you're adding 1, right? So that means that we're going to have to sum up all the multiples of n up to n minus 2 times n, okay? So that's the only catch in the problem, really, is this was a little sneaky the way they worded this. How did the square come into play? And it's just, it probably didn't bother y'all, but I had to think about it for a minute, what they really meant by it. Now, so not surprisingly, the n is going to factor out here. And so you're going to have n times the sum of the first n minus 2 natural numbers. Well, that should remind you of something. That's just the triangular numbers, if you've heard of that, or the sum of the first n integers has a closed form. Now, this is the form if you go all the way out to n, but it doesn't even make, as long as you have a concrete endpoint, you're doing good. But this says the sum of the first n natural numbers. I forgot to put an I in there. There should be an I index right there. But anyway, the sum of the first n natural numbers is equal to n times n plus 1 over 2. And that actually has a geometric interpretation. They're called the triangular numbers, that you can put at 1, 2, and it just forms a triangle at 1, 2, 3, and it ends up being a triangle. But the catch here is that we're not stopping at n like this does. We're stopping at n minus 2. But you can still use this formula as long as you know a clear endpoint in the summation. And so just like you would have n right here, you're going to have n minus 2. And just like you have n plus 1 right here, you're going to have n minus 2 plus 1 there, which is n minus 1. Okay. Now, so we know by the problem statement that all has to add up to 1176n. Okay. And so I've written that down. Now, I did a couple of steps here, folks, just to avoid a little bit of clutter. Notice that the n's, conveniently and almost necessarily have to cancel out. The n on this side and the n on this side are going to cancel out. It turns out 2 times 1176 is 2352. Okay. Now, and I did a little bit of the work for you here. When you multiply this out, you get n squared minus 3n plus 2. But when you subtract 2352 from that, you get minus 2350. Now, again, this was time consuming at this stage, but it turns out this does factor. This is a multiple of 50 here. 47 times 50 is that number. And then the minus signs work out like they need to work out here, right, folks? This is a 47 minus a 50 gives you the minus 3 right here, right? So it does turn out that it factors. And notice that there is a negative integer solution, negative 47, but we're dealing with natural numbers here. So negative 47 would be what they call extraneous. Now, so the answer is 50, and it's not particularly easy to check right here, because what that really means is you would have to add up the first 48 multiples okay? And that's, you know, that's quite a bit of work. And so, but what I'm going to do is I'm going to show you guys just kind of a special case of this, so you'll be convinced that it's true here. Let's see here. Let me see if I can get to the. All right. Now I just worked a much smaller special case, 6 squared. Well, 6 times 6 is a multiple of itself. And notice the way this one worked out, we had to chop it down by 2. And I don't have that screen up there for you, but what you have right here is 6 times 4, 6 times 3, 6 times 2, and then 1 times 6. That all adds up to 60. Okay. Now notice also, remember it's the multiples of n that were less than n minus 1. Well, our n here is certainly 6. 6 minus 1 is 5, so that's 5 squared is 25, right? Well, look, we started at 1 less. That's not always going to be 1 less, but you see, again, 6 minus 1 right here is 5. 5 squared is 25. Notice we started at 24, which is less than that. So that satisfies the condition we started with in the bigger problem. And then everything works out. It adds up to 60. All right. Now it turns out the sum of the first 4 natural numbers, if you add up 1, 2, 3, and 4, you don't need a formula to see that's equal to 10, right? And of course, 6 is in. So you get the truth here. It's 60 is equal to 10 times 6. All right. It's just I didn't want to go through. It would be very laborious on this one over here. You would have had to add up the first 48 multiples, all right, and then see if, you know, to see if everything agreed. So anyway, I hope that the problem was stated a little awkwardly. But anyway, I hope y'all enjoyed that. Thanks.